Hi, good morning. Hello. Uh, so, uh, I would like to start today's talk by reviewing a little bit what we had last week. Last week, I talked about the interaction picture, which is a midpoint between Heisenberg picture and the Schrödinger picture, which is facilitated by this unitary transformation to the states in Schrödinger picture. And the bottom line is that then in this new picture, the operators evolve just like in Heisenberg picture, but with the full Hamiltonian replaced by the free Hamiltonian. Okay, therefore, you could almost say that the law of the behavior of the fields is as if they are left alone with no interaction at all. However, the interaction happens in the evolution of the states. So on the other hand, the states evolve like in the Schrödinger picture, but with the full Hamiltonian replaced by the interaction Hamiltonian. I made a mistake last time by saying that this interaction picture is first proposed by Freeman Dyson. No, it is by Tomonaga, a very famous and actually very, very good Japanese sorry, I should turn into the full screen. A very, very good and very nice Japanese physicist. He shared the Nobel Prize with Schwinger and Feynman, the other two more renowned physicists in the West. However, I read some of the historic accounts during the week, and I found that actually Tomonaga made a lot of very, very innovative contribution to the physics QED. Okay, so yeah, Mr. Tomonaga. Okay, so now the action. Now that we have an interaction picture, then we can use this interaction picture to calculate the processes, like for example the scattering or the decay. I'm going to talk about scattering cross-section and the decay rates next time. Okay, stay tuned. But today I would like to follow up with this discussion of interaction pictures and the canonical quantization and arrive at the Feynman rule and Feynman diagram directly, at least the simplest parts of the Feynman rules. Okay, now since in the interaction picture the states evolve by the interaction Hamiltonian, so this is the equation. Therefore, we can define U, that's the evolution operator of the states, which is defined this way. I took this part I had covered already last time, so therefore I'll move on very quickly. And this U actually has satisfied a very, very similar equation as the state's evolution. The U, the time derivative of U is equal to minus IHI times U. And with this U, I can evolve a state from a certain time, for example, t0 here, to another time in the future, t. And if I approach and that t0 goes to minus infinity, that means it is the long past. And the t goes to the positive infinity, that is the long future. Therefore, we arrive at an evolution that take you from the long past to the long future. That is the typical setup for particle physics experiment. For example, decay. In the long past, there is a particle existing there, and then in the far future, it becomes other particle, so which is a decay. Scattering, similar. In the long past, we have two particles moving in their own direction and then collide and scatter into another kind of particle combination or particle states, and it is a scattering. So this U apparently contains all the information we need for predicting the particle physics processes. Okay, so let me go ahead a little bit more, then if this we act this U operator on psi, a state in the long past, and then if this combination is the state in the long future that evolves from a state psi in the long past. So if we want to measure, you use a physics experiment to measure the probability or amplitude of this state happening in another state phi, then in quantum mechanics, this amplitude is equal to the inner product of the two states. Okay, and if you write the amplitude in this way, you can easily find that it is actually a U operator sandwiched between psi and phi. Therefore, with this form, with this U in the long past, it is psi, and after the evolution from minus infinity to infinity, it becomes this combination. And then if you want to detect it as another phi, then you take the inner product of the whole thing. Therefore, it becomes the amplitude for this sequence equals to this. Therefore, all the information about particle physics experiments are contained in this operator, unitary operator. And so to recognize its importance, we usually give it another name, which is S. So this is S matrix or S operator. This S matrix or S operator takes you from the long past to the long future. So if I can solve this S, then I can answer almost all the questions in particle physics. Okay, now let's proceed to solve U and solve S. Of course, you can imagine that the U and S are not solvable exactly. However, this kind of, because the Hamiltonian, the interaction Hamiltonian usually is a very complicated thing. For example, here, the U consists of terms like lambda phi 4 plus G psi bar psi phi. So, well, I mean, this very complicated thing, since this phi field operator also could evolve in time. Okay, therefore, usually we in not just particle physics, in all physics, if we cannot solve the problem exactly, we usually use a perturbation expansion to at least get an approximation of the answer. So here what I'm going to do is to assume lambda and G are small. And if they are small, then it makes sense to expand U and later S also, the U in terms of powers of these small parameters. Okay, therefore I will write the U as U0 plus U1 and UN is proportional to lambda to the nth power or G to the nth power. Of course, you can see if these parameters are small, then the leading term will dominate. And then if you want to, but the leading term does not give you any answer, because if the leading term U0 means it is proportional to lambda to the zeroth power, which is equal to 1. Therefore, that U0 does not depend on lambda, G, these small parameters at all. And that means that's what happens to the evolution operator when there is no interaction at all, because you can set lambda and G equal to 0. Okay, so when you set lambda and G equal to 0, or put in another way, when you set lambda and G equal to 0, then U1, U2, U3, all the other higher terms vanish because there is no G. Okay, there is no lambda and no G. And therefore, U0 is the only term that is left. And U0, you can immediately guess the answer, 1. Because if there is no interaction, then the particle state will not change. Therefore, U, the evolution operator, must be equal to 1, the identity operator. Okay, so I got the U0 equal to 1, whatever the details of the theory. And then I plug in this expansion into the equation I'm going to solve. Just remember, to the left-hand side, the leading term 1 is independent of time. So when you take the time derivative, it vanishes. Okay, so the leading term to the left-hand side of the equation is U1 taking the time derivative. On the right-hand side, you have to remember H1 is proportional to lambda or G, the small parameters. Okay, that's the interaction coupling constant. Therefore, on the right hand, if the left hand side is of order 1, then the right hand side H is order 1 already. Therefore, the U must be 0th order. That is the U0. Okay, so that's the leading order solution of that's the equation of motion to the leading order in lambda and G. And we know U0 is just 1. Therefore, on the right hand side, it is minus IHI. Therefore, there is a very, very simple solution to this equation because it's almost a freshman physics. U is equal to the integral of HI because on the right hand side, there's no U at all, only the HI. HI is a function of the field, and the field is a function, are functions of time. Therefore, we can take integration over time and get you U1. Okay, so easy. This is actually very, very useful. It is as easy as possible. However, it is very, very useful. And I think it's first proposed by Born, okay, the very famous physicist who also proposed the probability interpretation of quantum mechanics. So again, Born approximation, and then if I send t0 to minus infinity and t to infinity, we got S. So that's the leading order expansion of S matrix, which is equal to minus I, the time integral of HI from minus infinity to positive infinity. Therefore, let me summarize this very, very beautiful equation in just one sentence. That is, in leading order, S equals time integration of the interaction Hamiltonian, HI. Okay, so we got the leading order already. So we are going to take this expansion to the second order in the next hour. So stay tuned. So S1 is this. And remember, HI is the Hamiltonian, which can be written in terms of the Hamiltonian density. So this becomes this. And we know HI, the Hamiltonian density, which is equal to the minus of the Lagrangian density. Okay, and therefore this term could be replaced by Lix. Why I would want to do that, the reason is simple. Because this integration is over d4x, and from minus infinity to positive infinity, which is Lorentz invariant because it treats the time and space equally. So it is Lorentz invariant, and of course it could be proven more rigorously mathematically, but usually when we see an expression that treats the time and space equally, we usually assume that it is Lorentz invariant. Therefore, if Li, the Lagrangian density, is Lorentz invariant, then S, the answer we got, is Lorentz invariant. That's the beauty of the whole derivation, since at the end of the day, even though in between, look at the expression in between, we have a time integral of HI. Well, HI is not Lorentz invariant. dt, the time integration, is not Lorentzian invariant either. But however, in this combination, as I show here, the final answer is actually Lorentzian invariant. Okay, even though it's not clear in the process in between. However, the end result we know it is Lorentz invariant. Beautiful. As long as you keep the Lorentz density invariant, then we got a Lorentz invariant solution for the S matrix. Bingo. Okay, so let me give you a very, very simple example of this expression of this answer. Let me introduce a model. We call it ABC model. ABC model, actually, it is a model you can find in Griffith's book. And this ABC model, as I explained earlier in my particle physics introduction course, it is actually very, very similar to QED. The only difference is that there are 3 different particles, and they are all scattered, so that we don't need to worry about bispinner structure, something like that. However, in this ABC model, almost all the diagrams and all the process in QED, you can find corresponding parts in this very, very simple ABC model. Of course, the answer is different. The final amplitude would not be the same due to the bispinner structure. However, you can learn how to draw the Feynman diagram and how to write down Feynman rules in this very simplified model. Okay, so just like the name implied, ABC model consists of 3 different particles, A and B and C. Okay, and therefore after some quantum field theory, you know that each particle corresponds to a field. Therefore, we assume that there is a field for A, there is a field for B, and there is a field for C. To simplify the notion, the notation, I will just call phi A as A and phi B as B. And then in this model, there is only one interaction term in the Lagrangian density, which is G times A times B times C. So this term, of course, Lorentz invariant, because A, B, C are scalars. And what else? In this interaction, the field A and field B and field C, everybody gather together, and there's an interaction between them. That's the rough idea of this interaction. And G is a constant. We usually call it coupling constant. And what I'm going to do is to do the expansion, the perturbative expansion in G. Therefore, G must be slightly small. It could not be large. If G is large, what I'm going to get does not make sense at all, because there will not be a perturbation expansion. Okay, now use this Lagrangian density. Let me tell you that I can write the transition amplitude for A decay. For example, A decays into B plus C. Then we can put everything I talk about today into the calculation. First, the transition amplitude is this matrix element U between A to BC. Again, let me emphasize again, the state of the particle is A in the long past. However, after the decay, it becomes B and C. So the state becomes BC in the long future. And in between, there is a time evolution. And if let this time evolution to evolve from minus infinity to infinity, then it becomes S, the S matrix. Okay, then according to our perturbation expansion, to leading order, S is equal to the space-time integration of the interaction Lagrangian. And you just plug in what we have here. You got G, A, B, C. And therefore, what you need to calculate is actually, for the leading order, is actually this. A, and this operator sandwich between A and B and C. Okay, so now it's the most actionable part of. I'm going to show you a cartoon and how to show you how this works. Now, and this is the part I like that I like most in presenting the QED. And you see action. Somebody kills somebody, somebody kills somebody, and in the end there is something left. That's the idea. Okay, so in the middle of the page, I showed you the matrix element I'm going to calculate. That's the matrix, and between these two states. But remember, this A, sorry, not yet. This A and B and C are operators, and in interaction picture, they only evolve by the free part. Therefore, I can write down A in terms of a Fourier transform A and A dagger multiplied by their corresponding plane wave solution. And let me emphasize, this plane wave is written in a Lorentz invariant form. That will be very, very helpful in our calculation later. Likewise, BE could be written in terms of this Fourier transformation. Fourier transformation. C, again, is the same. The structure is very simple. If you disregard all this integration and plane wave solution, because they are all numbers, in terms of operators, the structure is very simple. It is equal to A plus A dagger, B plus B dagger, C plus C dagger. In all, there are 8 terms after you expand this multiplication. And for example, however, all the 8 terms are actually only consist of one term which will not vanish, which is an A from A dagger, A operator from A, and a B operator, a C dagger operator from C, and a B operator from B. The reason is simple. It is hard to present in online lecture. However, you can see very clearly if you expand all the A terms. For example, you got A, B, C. However, this combination consists of 3 annihilation operators. So you need 3 particles to annihilate. However, I have only 1 particle on the right-hand side. Therefore, after A annihilate this particle, it becomes vacuum. And any operator acting on vacuum becomes vacuum, okay? Becomes 0, so it vanishes. So I leave it for your own to convince yourself that only 1 term that will survive at the end of the day. That term is A from A hat and B dagger from B, B dagger from B and C dagger from C. The idea is simple. This A could annihilate this particle, and this B and this C could create these 2 particles. Okay, let me put the mathematics more clearly. So if for this surviving term, A from A hat will annihilate the A state by this expression. So the right-hand side becomes 0. And C create this particle, okay, and therefore when this C acting to the left-hand side, the C dagger becomes C, and this C dagger acting on a C particle state will again give you vacuum. Finally, the B is B dagger. However, acting on the left-hand side, it becomes B. So B acting on a particle B state will again give you a vacuum. After all this manipulation, you got the vacuum on the right-hand side and vacuum on the left hand side. So it is the inner product of a vacuum and a vacuum. And of course, it is equal to 1 because vacuum is normalized state. Okay, so I leave the detail to you. However, I need to remind you one thing. When you annihilate the particle, because A, in the expansion, the momentum need to match the momentum of the N particle. For example, if this A is going to annihilate this A particle, the momentum here must be equal to P1. So that's what I express here. So when A acting on A, it must be P equal to P1. Otherwise, it will vanish also. Likewise, the momentum of the C dagger must match the momentum of the C particle. The momentum of B dagger must match the momentum of the state. Okay, it's a little bit messy on the screen. However, I hope you will do the maneuver yourself at home. You hope you will convince all the rest terms will vanish and only one term survive, and that one term will give you extra, that the only surviving term is A, B dagger, C dagger with the momentum P1, P2, and P3. Therefore, when you finish the annihilation and creation, we are left with exponential from the plane wave numerical factor. Okay, so from this we got the exponential minus I P1x, and from this I got exponential I P2x. From this I got exponential I P3x. So combining the three factors together, I get exponential minus I P1 minus P2 minus P3 times x. But remember, I need to take a space-time integration. And when you take a space-time integration, this thing simply becomes delta for P1 minus P2 minus P3. And this delta function enforces the momentum conservation. It asks the P1 and P2 and P3 to satisfy the P1 equal to P2 plus P3 rule. Okay, that is the momentum conservation law. Okay, and therefore we are done. So the only factor remain is the I and G. Remember, there is a I and G here. So there is a I and a G and a delta function. Okay, that's all we have for this amplitude. Okay, and if you have learned already some Feynman rule, you immediately recognize this is the Feynman rule for this vertex. That is, we can represent this amplitude in terms of this vertex, where an A annihilated created a B and a C. Okay, and the Feynman rule corresponding to this vertex, and it is called vertex diagram. And if you the Feynman rules corresponding to this vertex diagram is I times G and the delta function. Okay. Therefore, this is a Feynman rule corresponding to this vertex. Okay. That's, and probably I should say this is the origin of this process. Okay. And the key part is the key reason or underlying reason for this vertex is, of course, the interaction Lagrangian. Remember, we started with this interaction Lagrangian GABC. And let me remind you again, when I do the calculation, I plug in AA dagger for A, BB dagger for B, and CC dagger for C. I remind you already there are in all A terms when you make the expansion. However, most of them will vanish. But on the other hand, this diagram could represent 8 different kind of diagrams, because in what we have here, it is A decaying into B and C. However, if you pick this for example, C and the combination of C, A dagger, and B dagger, then the combination will annihilate a C, create a B, and create a A, which is a decay of C going to A and B. Okay, it is a decay of C going to A and B. Therefore, and of course, some of the combination does not work at all. For example, if you have C daggers, A dagger, B dagger, you need to create three particles. That means this particle in, and particle in. Three particle, out. Sorry, this particle out will create a particle. So it's particle out, and particle out. Okay. However, this combination is valid. However, remember we have a momentum conservation. So the momentum conservation does not allow the C daggers, A dagger, B dagger to survive in any case. Therefore, I have to remind you that this diagram actually consists of 8 diagrams. That's the beauty and economy of Feynman rule and Feynman diagram scheme, that a simple diagram actually represents in all 8 diagrams. Okay, that's the beauty of it. And what else? And there is some interesting thing that when I do this calculation, I make the integration over x. That means from minus infinity to infinity. That means this x, the position of these fields actually could be anywhere and any time from minus infinity to infinity. Okay, so the essence of a term like this is at that point x, A field, B field, and C field get together. Okay, but where that point is, the x is, actually there are mountains, so many possibilities. You need to sum over them. It is almost like a double slit experiment. When there are 2 slits, the wave can get through. You have to sum over the amplitude that the wave passes from 1 or passes from 2. Okay, so that's essentially the same thing that represent the superposition of amplitude from various possibilities for this decay to happen. But when the interesting thing is that after you carry out this integration, it does not feel like you need to worry about where that things happen at all, because after the integration, it only gives you a delta function, and that delta function has a very simple physical meaning, which is the momentum conservation. Therefore, in momentum space, the factor is actually very, very simple. That's the beauty of doing this calculation. So that's the beauty of doing this with A, B, C, the state of A and B and C, from states with positive momentum. Remember, when I go back to our calculation, the matrix element, I start from a state with A in momentum P1, B and momentum P2, C and momentum P3. And we do that because in this momentum space, the result, after you carry out the integration of space-time, the final result is actually very, very simple. So I will say that in momentum space, the factor for a vertex is simply a constant. Okay, that wouldn't be the case if you try to calculate the process with a specific place or specific time for A. Okay, then that would be very, very inconvenient when you try to calculate the amplitude. Okay, so I usually told students that in momentum space, the Feynman rule becomes so simple. However, the idea becomes obsolete because in momentum space, you cannot say for sure where this interaction occurs because it has been integrated over. Or put in another way, this interaction could happen anywhere and any time, and it obscures the physical meaning of this interaction. Okay, so we sacrifice, in a certain sense, we sacrifice the physical meaning for the simplicity of a vector. Because again, in momentum space, the vector is simple, but the physical meaning is lost. It will happen again when we do the next order expansion and introduce the propagator. The propagator, if you do it in in real space-time, it becomes very, very complicated. But the meaning, physical meaning, is clear. However, if you want a very, very simple expression, you go to the momentum space. But by going to the momentum space, the meaning of the propagator, usually we mean propagate from here to here, the meaning got lost. Okay, it's a very interesting thing I will show you next week when we get to the propagator. Okay, so therefore, now, let me summarize my introduction of the first term. And so this is the vertex, the interaction Lagrangian, and it corresponds to a vertex. And the process that can occur could be described by a Feynman diagram. And for those processes that cannot be described by a diagram, cannot occurs at all. Okay, oh, sorry, I missed a cannot here. Okay, so now let me say it again. The process that occurs could be described by a Feynman diagram. And for those processes that cannot be described by a Feynman diagram, cannot occur at all. For example, if you ask me, is it possible for A to decay into B and B? To the leading order, it could not, because there is no vertex like ABB. Remember, if you want a vertex ABB, then you need the interaction Lagrangian, which is the multiplication of an A and a B and a B operator, which we did not put into our model. Okay, therefore, because this diagram does not occur, so this process will not occur in the leading term. Okay, so diagram and physical process has a one-to-one correspondence, and a diagram with the amplitude has a one-to-one correspondence. That's the key of the Feynman diagram scheme. I hope you appreciate this. Before I let you go, I would like to, for example, let me give you another example, which is also a very useful and famous theory. We usually call it lambda phi 4. And here we only have one field, which is phi. And therefore, this phi will have a dagger plus a dagger. And then this phi to the fourth, you can expand very easily. And I hope you will appreciate very easily then this interaction Lagrangian will correspond to a vertex because of 4 legs, and every leg corresponding to a phi. But remember, every phi could represent 2 things. One, annihilation of particle by A. The other is the creation of a particle represented by a dagger. So in all, there are 16 diagrams that is combined into one very, very simple vertex. Okay, how? I hope you appreciate the correspondence between Lagrangian, vertex, and amplitude. That's the key I would like to draw today. Now, before I let you go, probably I can still talk for 10 more minutes. I will start the second order, but I will finish the second order calculation next time. Okay. Second order, well, easy, because you just plug in the second order to the left-hand side and calculate the second order expansion of the right-hand side. So it's so easy. U to the second order will be U2. On the left-hand side, again, remember HI is of order 1, therefore U must be also order 1 to match the left-hand side. So it is U1. But do we know U1? Yes, we know U1 from the calculation earlier of the first order. That's the key of the perturbation expansion. All you need for certain order of calculation has already been solved in earlier calculation of less order. That's the key of the perturbation expansion. And just plug in the answer. This U1 is equal to the integration of the Hamiltonian density, the Hamiltonian, okay? So this U1 will be this. And we can also use the integration to solve this equation, because on the right-hand side, this t and t are the only variable that correspond to the derivative. So U2 will be equal to this expression, the integration of dt double prime, and we replace this tt by t double prime, okay? So this is originally t, this is originally t. Now I replace it with dt double prime. After integration, I set the limit of integration at t, okay? So look at this structure. The structure is that this is an expression of two identical interaction Hamiltonian, however at different time, t prime and t double prime. So that's why the order of the time becomes very, very important. However, please observe that in this expression, t double prime is the upper limit of the first integration, t prime. Therefore, t double prime must be larger than t double prime. That means the left-hand side, this hi, the first hi, is always later than the second hi. That's the key observation I think Freeman-Dyson used to derive the very, very famous equation, very famous solution of this equation. This is by, oops, I didn't have Freeman-Dyson here. Yes, I have Freeman-Dyson picture. Let me finish it because I have only 5 minutes left. So let me finish very fast so that you can try to figure out yourself at home. But I will come back to review this part again next week. So I got an expression, though very complicated, for U2, which is this. Okay, and let me remind you that on the t prime, t double prime plane, the integration range is the upper triangle, because as I remind you, t double prime is always larger than t prime, because t double prime is the upper limit of the first time integration of t prime. Okay, however, remember t prime, t double prime are just dummy notations. I can simply exchange them, that is, replace t prime by t double prime and replace t double prime by t prime, and the answer will be the same, because there is nothing essential about these two notations. So I replace t double prime by t prime. We replace t prime by t double prime. I get this expression. Remember, they are the same, so I can add the two terms and divide it by 1/2 and get the same result, because this is equal to this. That's the point. Now, the key observation, let me read. The two terms on the right-hand side are the same. However, if you look at this second term, the integration, if you again see it from the T prime, T double prime plane, the integration range is actually the lower triangle here. You can figure it out yourself. The range of integration of the second term is the lower triangle. Therefore, the integration, if you simply look at the integration range, then this range and this range would make up the whole square. However, on the second term, actually I switch, but the integrand are different. That here is T double prime, HI T double prime, HI T prime. But here it is HI T prime, HI T double prime. Actually, I switched the order. You compare the two. But by switching the order, what I did is actually keep the later HI on the left hand side. Observe that here T double prime is the later time, okay, because T double prime is always larger than T prime. But here, the T prime, according to the integration range, T prime is always larger than T double prime because it is in the lower triangle. So, again, the left-hand side, H is the later Hamiltonian, and this is the earlier Hamiltonian. So therefore, I can conclude that the integrands could be summarized in just one formula, which is HI times HI T double prime and HI T prime. The earlier under the condition that earlier HI always placed left. So in the case of T double prime larger than T prime, we got this. In the case of T prime larger than T double prime, we got this. Perfect. So by this notation, by this condition, I can write the two terms in a single formula. But now the integration is over the whole square. Okay, so why not introduce a notation for this condition, which is the time order product of two operators, okay? That is, we always place the later time at the operator at the left-hand side. And therefore, this U2 then has a very, very formal solution, which is this, okay? I'm going a little bit fast. And then if you send the T0 and T to infinity, you got the S matrix. And if you replace the HI with the Lagrangian density, you get this expression, which is the formal solution for our S matrix. Let me remind you again, the key is that this whole expression is Lorentz invariant. Okay, I'll come back to tell you to slow down the presentation a little bit next week and give you some more detail about our derivation. However, you are encouraged to study this part on your own, and you will see it's a very, very beautiful derivation. Okay, so see you next time.